Welcome to Math 104, where we're talking about different types of regressions. Today's focus in this video will be 6.2, where we talk about cubic and quartic modeling. So with this knowledge, we have already watched the first few videos on how to enter in a regression, whether or not it's linear or quadratic. We've also talked about how to find your average error. So if you have not watched those few videos, please go back and watch those, because we are just going to kind of breeze through and look through the cubic and quartic modeling in this particular video. So our problem here just says the percent of US population that were foreign born in the selected years from the 1900s and projected to 2020 are shown in the table below, where X is the number of years after 1900. So we already know this statement to mean, let's see, can I highlight that? There we go. This statement we've seen before, where we know that for the year 1900, we're talking about X being 0. So it's representing that year, which means that we're going to go ahead and replace this 1900 here with the X value of 0. And we're going to do it again with 1910. So the difference between 1900 and 1910 is equal to 10. So that's why you're going to see over here on the right-hand side of my screen, we go from 0, 10, 20, and 30, and so forth. So that's why this here is going to be 20 and 30, and you'll keep going. Now, in a previous video, we said, hey, I don't mind our computer. It just thinks it'll show the first few values, and then it'll kind of pop up as you go through. So you can hit enter, but keep in mind, we go from the increments of 10. And then from the year 2000 to 2005, there's only a 5-year difference. So that's why we go from 105, and then there's 4-year difference, 109, and then 1 year. So be super careful with these values as you're clicking through. Don't hit enter too many times. Otherwise, it's going to pull up with inaccurate data to ours. Because there is a lot of data, though, be sure you are double, if not triple, checking that your Y values are correct as they are on the other side. We've also talked about how to find an accurate window. So please watch previous videos on how to find a good window. So you'll notice that our data is over here on the other side. I'm going to shorten that up for a second. Now, what models do we think could work? So again, taking our previous knowledge from our Math 104 class, do we think it could be, so the models that we have seen so far, linear, quadratic, we've also learned about cubic, quartic, we talked about exponentials and logarithms in chapter 5, also logistic functions in chapter 5. So we've seen all of those here in the last few videos. So what do we think this one could be? Now, if you are at all confused, the ones that we've graphed so far, this one, number 2 being linear, right? You can always make a comparison. Do we think that line is going to be a good fit for a curve data? No, definitely not. Linear would not work in this case. We have too many turning points. Too many turning points. We can also try and graph, so we can take that one away. We can also try and graph your quadratic. So again, against this curve, we only have 1 turning point, but we can see clearly 1, 2, 3 turning points. So quadratic has 2 few turning points, or not enough turning points. In previous videos, we talked about the number of turning points and how to find the most accurate model, or the number of turning points with a certain degree, right? So if you already know what could work, we can certainly put that there. Now, if we're between 2, if we don't know whether it's cubic or quartic, we can certainly put those 2 in. That is what this video is all about. If we don't know exponential, right? Exponential is the graph that kind of goes up super quickly or down super quickly. or logs is the one that starts down low and then skyrockets and then flattens. Or logistic is the S-shaped curve that starts kind of down low, comes up and makes that S shape. So unfortunately, those ones will not work. We'll take a look at other models that will be an exponential log and logistic. So this one, let's try to graph a cubic and a quartic model and see which one would be better. So as always, we're going to start with y sub 1. And that little squiggly again, how to get there is you're going to be holding down your shift key and then clicking that key right there. So you have ax sub 1. And because we're talking about cubic, we're going to cube it. And then so as we're going to go through, we're going to still be using your A, B, C's, and we're just going to tick downwards from there. So plus bx sub 1. So 1 less degree being 2 plus c x sub 1. You don't have to put your exponent on this one. And plus d. So you'll notice here, just double checking, these values aren't all that great, or sorry, against your graph, it's not all that great. We don't actually get to see your other turning point. It's perhaps up there a little bit further. Actually, perhaps over here, it turns around, right? So this isn't the best model. So we could, if we wanted to, stop there, but I'm going to just show you again some other ideas and information that could actually rule it out like you would in our project that is coming up. So first off, your correlation coefficient, again, we want this to be as strong as possible, so as close to 1 or -1. Now this has actually an R squared, and what we need is to have this R, your correlation coefficient. So we're going to be using Desmos scientific calculator. And what we're going to do is we are going to take the square root of this value. So if this is squared, we want to undo it with the square root. So 7698. So we're going to write the square of 7698. So it is a little bit better. Your cubic has an R, your correlation coefficient of 0.8774. It's not actually all that strong because, again, we want to be as close to 1 and -1 as possible. Visually, it does not please the graph. So visually, the majority of the data is missed by the curve. Your correlation coefficient is not close to +1 or -1. And the last is going to be your average error. So to get your average error, we're going to first select the residual plot. Now this is going to be located in E3. So as you're going through, the reason for it is, if you're following along with my video, is that we have more residual plots, just that I haven't plot them. So when we go to find your SSE, so we do total E sub, and then we're going to type in 3. That's the one that we're going to do against this cubic. And then we're going to square these values. And then to get your average error, we're saying A sub E is equal to your square root, oops, of your SSE divided by count and X sub 1. So your average error is 1.347-ish, which isn't, again, not horrible. It doesn't exactly give us a great fit though, because again, visually that's not great. And with it being 1.3, we can also compare that to these values here, right? Your values aren't necessarily going up all the way by 1 or -1, right? There is a little bit of jump here and again here, but for the most part, we have very, very small increments that we are increasing and decreasing by. So that just means your average error of 1.3 or 1.4 is actually going to make a big difference. So obviously, cubic is not a great fit. we'll also type in your average error of 1.3, I think we said, or 3.4 is big in comparison to the Y value increment. I cannot spell increment. So now let's try it again with a quartic model. So we will go ahead and deselect your cubic, and we're going to graph another one. So let's go ahead, and if you want, you can also copy and paste some of these values. So if we wanted to, the reason for that is that all we're doing is we are changing your exponents. So we're going from 4 to 3 to 2 to 1. And then normally it would be E kind of in the to follow along with like our alphabet, but our computer doesn't know the difference between the letter E and the significance of this irrational number E. So we're actually going to say plus F in this case. So, and I'm going to get rid of the blue dots here. So I'm just going to deselect that blue, and that way it's a little bit more pleasing to the eyes visually. So what do we think about your graph against the data? So this, starting off, the Quartic is a better fit. It does miss a few points. You'll see here, 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 and a few points over here. So we can't say it's a better fit. It's not going to be a perfect fit, but it is a good fit, we can say. Good fit visually. It hits the majority of the points. What misses? Let's say 1, 2, 3, 4, 5, 6-ish points. We can look at your average, or sorry, your correlation coefficient. Again, this is not the correlation coefficient. We're going to have to square root that value. So 9875. 9875. So that compares really well to what we're seeing in the visual sense. So R is 0.9937. So again, this is being close to +1. Means that we are more accurate, or we will have a better fit, or we're closer in relationship to the X and Y value. So again, that actually matches with what we're seeing. So we want that to be as close as possible. Now, when we go to find your average error, we now need to switch your residuals. So where our residuals are going to be in E4, and you'll notice that we want these black dots to be as close to the x-axis as possible. So we're going to change that value, and then we have your average error is 0.31, depending on how we want it to round, which again is actually pretty good in comparison to our last one of 1.34, so definitely under that value. This value is better than before. So if we're picking between these two models, the Quartic model would be a better fit. Okay, so one tidbit, again, be super careful with your Quartic model that we're not doing plus E, it's going to be plus F. And again, here are your A, B, C, D, and F values that we would be plugging into your equation here.